Hello, my name is Gedalia Knizhnik, and I'm presenting the paper I wrote with Dr. Mark Yim, titled Amplitude Control for Parallel Lattices of Docked Modboats. We at Penn have developed the Modboat, a surface swimmer powered by a single motor, meant as a low-cost platform for ocean research and maintenance. The modules can also dock together and reconfigure to form mobile landing platforms for drones or rescue vehicles, build bridges for land vehicles, or to form mobile aquatic manipulators. This video from underneath demonstrates the basic propulsion principle. The oscillation of the motor causes the passive flippers to open in a paddling motion that we can adjust for propulsion and steering. The mechanism is contained within the footprint of the top body so that the modules can swim side by side, as in this figure. The protruding tail tip can then be used to undock the passive magnetic docks without additional actuation, as shown here on the right. That's where the problem happens. Let's say we formed our mobile manipulator and we want to swim to the target. Well, how do we do that without accidentally bumping two tails together and disrupting the whole lattice? This forms a significant constraint on the allowable motion. Here on the left is a video demonstrating this. Let's say we're swimming along in the down direction and we decide to brake, naively assigning the outer boats to thrust up and out. This naive assignment immediately causes the structure to break, and it's what we want to avoid. That's why, in this work, we present a strategy for controlling parallel lattices, i.e. modboats docked in a horizontal line, that guarantees that there will be no unintentional undocks, while also maintaining control of the structure. Essentially, by forcing all boats in the structure to stay in phase with one another, and restricting the center line, which corresponds to the average force direction, to be either forward or backwards, we can guarantee that the tails will never collide, while also maintaining controllability as long as the structure is at least two boats wide. Now, when we choose to brake, we know that the outer boats must thrust straight back, or up in the video. The boats transition smoothly, and the structure stays together. With this strategy, we can assign arbitrary surge forces to each boat in the lattice to thrust the structure, and the lattice can be torqued by the lever arm each module has relative to the lattice's center of mass. So, for a desired force and torque applied to the lattice as a whole, we can use the Moore-Penrose pseudoinverse to assign forces to each module that most closely mimic the movement of a rigid body. This prevents undocking due to excessive movement on the passive magnetic docks. As a result, we can effectively control both the surge velocity and yaw angle simultaneously for parallel lattices of arbitrary dimension. Watch how all of the lattices stay abreast of each other as they swim up in this video, maintaining the same velocity regardless of lattice dimension. As the lattices turn, we notice that the smaller lattices do turn more quickly, but all of the lattices are able to successfully execute a 180-degree turn within a few seconds of each other. Finally, they stay pretty much in sync as they swim back, maintaining the same velocity on the return journey. Stay tuned for future work in which this control strategy is effectively applied to non-parallel lattices as well. Thank you for watching, and please reach out with any questions or comments on this work.